right? Plus sine of 2 times omega t plus theta v sine of theta. Yeah? And next, what's happening is you can separate these two and you see that the voltage times the current times cosine of 2 times omega t plus theta v plus cosine of theta. Yeah, so that's this portion here. I'm saying, okay, this portion here, let's neglect this portion for now. We're going to say this is the real power portion. Power real, R. Yeah? This is the energy transferred. Let me see how we call it here. We say that this is the energy transferred into the circuit. Energy flow into the circuit. Okay? Similarly, they call this X. Usually means reactive, and it is reactive. Voltage, current, sine 2 omega t plus theta v sine of theta, and they say this is the energy. They say this is the energy borrowed. Energy borrowed and returned by the circuit. So why do we say like this? Because, for example, you have capacitor. Capacitor, does it consume? It just takes in the voltage, stores it, charge up, and then release after, right? So it's just like a storage element and then releasing. It's like a spring, right? You can think of it like that. You can think of it like that, right? But resistor just dissipates this energy through thermal heating of this resistive, the conductor material. And this is why you're actually into the circuit, and this is just borrow and return for Px of t. Yeah? But it's still very, very important to analyze this type of power, because it's still unwanted power that it's wasted. It's not to any use to us, right? A good analogy that I watched in a video is if you have, for example, you pour a cup of beer, right, into some container, and then the actual beer is maybe up to here, and then you got a bunch of foam here on the top. This foam is reactive. Stuff you don't want, but it just happens to be there. But it takes up space in your cup, and you can't fill up your beer that much. So that's a good analogy there. Continuing from there, we got that out of the way. And this is, yeah. And by the way, P of t by itself, this one here, P of t, is called instantaneous power. Similarly, this is the real component of instantaneous power. So P of t is instantaneous power. Similarly, this is the real component of instantaneous power. Now, what happens is actually this VI, it's going to expand to both. Okay. So now what happens is, if you notice, this here has got two terms here, 2 omega t plus theta v, and this one, yeah? But what happens is, when you find power, you find average power, expected value. And the average of a cosine wave is zero. Why? Because let's draw it, and you'll know why. If you got a cosine wave, very roughly, if you got a cosine wave, that's something like that, for example. I don't know, right? This maybe is 1, and this is -1. What's the middle point? 0, right? So the average is 0. It's fluctuating between 1 and -1, so the average is the midpoint, 0. So the expected value is going to be 0. But the thing is, you only consider, so you say, okay, this one's going to be a 0, right? But this one, cosine theta, you think, oh, it's going to be 0. No, because theta is like a constant, actually. It's a constant, because if we consider this as like a random variable process, you can say that, oh, that this one is changing. It could be anything, right? Theta is a constant. It's not changing. So cosine of theta really is just a constant. It's just a number, right? So you don't see that it has a certain... The average and expected value of a constant is just a constant itself in mathematics, right? So actually your PR of t, it reduces to just simply RMS value of voltage times RMS value of current cosine of theta. Okay? And this here is called the real power. And cosine of theta is a special significance, and it's called the power factor. Power factor. Okay? Various machinery have various power factor. Okay. This VI is absorbed by the resistive part of the load. Why? Because the resistive part of the load is a real component. We consider it as a real component. It's got a real resistance. Okay? Or you can say a real impedance. Yeah? And you know that when the current is lagging, we said it was inductive, the voltage. When current is lagging voltage and voltage is lagging current, it's a capacitive. Okay. Yeah. And similarly, you can look at the px of t, which is the imaginary component, or reactive component of instantaneous power. And that is equal to V times I times sine of 2 times omega t plus theta V sine of theta. Yeah. And this VI is actually, what we call reactive power. It's got the units technically same as the real power, but we change it up so we can know the difference. We put this in VAR, what's called VAR. Well, in reactive power, real power, you have watts, but this one is VAR, which means volt amp reactive. But you see in like the nameplates of like machinery, you'll see like it's VA. You know that's a reactive power. If you see something's watts, that means it's a real power. Okay. Now, lastly, we'll conclude this video with some observations. This is directly from the textbook, but it's just some things in case you're not a fan of reading, or you're more of an audio person or something. Some observations. For a pure resistor, the impedance is 0 and the power factor is unity. So for a pure resistive, you can see for a pure resistive element, it means impedance is 0. I actually want to correct myself then, what I previously said then, right? It's purely resistive, right? No impedance. And the power factor is unity. What does that mean? Theta is 0. Because cosine of theta we define as power factor. So cosine of 0, it means 1. Yeah? 1 means unity. Okay. So it also means that the apparent power and real power are equal. They're equal. All the energy is transferred thermally. And now the next thing, the next observation, just bear with me, there's two more. This observation and another observation, that's it. If the circuit is purely inductive, sorry I keep repeating myself, but I just want it to stick easier. If the circuit is purely inductive, there is no transformation of energy. There is no transformation of energy. Transformation of energy from electrical to non-electrical form. From electrical, so what does that mean? To non-electrical form. So what does that mean? It just means, like, you know how we said for the purely resistive, it means we convert to thermal energy, right? Because the resistor heats up. Yeah, the resistor heats up. It's a conversion from electrical to thermal. But here it's just no conversion between electrical and non-electrical. A good analogy for an inductor is it's like a propeller device. Like you've got a river, and this is your current, and you've got a propeller device here. Propeller device, right? So as soon as you apply current, the river starts flowing, this starts rotating, right? Now I cut off the power supply, no more current, so the water is still. But the inertia will make this thing continue to rotate, yeah? So you still have sort of like a simulation of flowing current for a certain amount of time, and eventually it'll stop, yeah? And you can think of a capacitor as like a spring. You store voltage into it. It's basically like you're compressing the spring. Once you stop, you cut off the voltage supply, spring will release in the opposite direction, and it will release the voltage out, right? That's something to note there. Lastly, if it is purely inductive, I said that, purely capacitive, current leads voltage, yes. By 90 degrees. Okay? And two more things. So P of t when it's greater than 0 and P of t when it's less than 0. What do those mean? When P of t is greater than 0, that means that energy is being stored in the inductive load, and if it's less than 0, it means energy is being released from the magnetic field. Okay, so that concludes this session here. I hope you enjoyed this. It was just power in a single phase circuit, real power, reactive power, and complex power. The next session we'll see what the textbook's following. We got to go through chapter 2 first, and then, which is mostly review, and then we can move on to chapter 3 and 4. I'll do an example, I believe, in the next section of this topic.